In this video, I'll discuss moving between geometric and component representations. We will frequently need to decompose a vector into its components. We will also need to reassemble a vector from its components. The figure to the right shows how to move back and forth between the geometric and the component representations of a vector. As stated in the top of the figure, the magnitude and direction of the vector A are found from the components. In this example, the magnitude of the vector is equal to the square root of the sum of the squares of its two components. And the angle is given by the arctangent of the ratio of the opposite side over the adjacent side. We see that the components of the vector A are found from the magnitude and the direction. If a component vector points left or down, you must manually insert a minus sign in front of the component, as done for b sub y in the figure to the right. The role of sines and cosines can be reversed depending on which angle is used to define the direction. In this example, we see that the sine of the angle phi is equal to the x component over the hypotenuse. If the angle was inclined with respect to the horizontal, b sub x would be equal to b cosine phi. The angle used to define the direction is almost always between 0 degrees and 90 degrees. In this example, we want to find the components of an acceleration vector. Seen from above, a hummingbird's acceleration is in magnitude 6.0 meters per second squared, and its direction is 30 degrees south of west. We want to find the x and y components of the acceleration vector. We visualize this example with the figure to the right. In the figure, we see that the y component of the acceleration is plotted versus the x component of the acceleration. So we have for our axes a sub x and a sub y. The x component is negative because it's pointing to the left, and the y component is also negative because it's pointing down. We can solve for the components of the vector A by using the trigonometry shown in this figure. Notice that the plot, in constructing the plot, the units of the vectors on the axes are shown. So when we solve the acceleration vector, points to the left in the negative x direction and down in the negative y direction. So the components a sub x and a sub y are both negative. So using the trigonometry, we see that a sub x is equal to minus a times the cosine of 30 degrees, since the cosine of 30 degrees is equal to a sub x over a. And when we evaluate that, ace of x then is equal to minus 6.0 meters per second squared times the cosine of 30 degrees, which is equal to minus 5.2 meters per second squared. Similarly, the ace of y is equal to minus a sine 30 degrees, and when we evaluate that, it's equal to minus 3.0 meters per second squared. Now let's assess the example. The units of ace of x and ace of y are the same as the units of the vector A. Notice that we had to insert the minus signs manually by observing that the vector points to the left and down. In example 3.4, we want to find the direction of motion. Shown in the figure is the car's velocity, vector v. We need to determine the car's speed and direction of motion. We visualize this example with the figure to the right, which shows the components v sub x and v sub y, and defines an angle theta with which we can specify the direction of the motion. When we solve, we can read the components of the vector v directly from the axes. V sub x is equal to minus 6.0 meters per second, and v sub y is equal to plus 4.0 meters per second. Notice that v sub x is negative. This is enough information to find the car's speed, which is the magnitude of the vector v. Using the Pythagorean theorem, v is equal to the square root of the x component squared plus the y component squared. And when we put in the numbers, we see that it's equal to 7.2 meters per second. Then using the trigonometry, since the tangent of theta is equal to the opposite side over the adjacent side, then theta is equal to the arc tangent of v sub y over the magnitude of v sub x, which is equal to the arc tangent of the ratio 4.0 to 6.0, which is equal to 34 degrees, where we were careful to specify degrees when we used our calculator. The absolute value signs are necessary because the x component of v is a negative number. The velocity vector v can be written in terms of the speed and the direction of motion as vector v is equal to 7.2 meters per second, 34 degrees above the negative x-axis. And this concludes this video.